Hi everyone, welcome to the video, and today we'll be talking about number systems. Why are number systems important? Well, in the programming world, we use number systems for different applications such as FPGA programming, which are used for satellite communication, and embedded systems such as in the automotive industry and home appliances that we use daily, some examples being your microwave, your refrigerator. So the decimal number system is a number system we were taught in elementary, which consists of numbers 0 to 9 for a total of 10 numbers. Binary, on the other hand, consists of only 0 and 1 for a total of 2 numbers. The hexadecimal number system consists of a combination of letters and numbers, numbers 0 to 9 for a total of 10 numbers, and letters A to F for a total of 6 letters. This adds up to a total sum of 16 characters used for the hexadecimal number system. In the far right, we could take a look at how the value 1 represents high, true, or on, but the value 0 represents low, false, or off. You also see some examples of ones and zeros, and I'll explain in a bit why each number is underlined. So in binary, we have a storing element which is called a bit, and that bit could only store either a 1 or 0. Again, back to binary, only ones and zeros, no other value than that. 4 bits is equivalent to 1 nibble. It's just a wording. 8 bits is equivalent to 2 nibbles or 1 byte. Okay, so if we have 4 bits, the least significant bit would be on the far right. The most significant bit would be on the far left. When it comes to programming, we always start off with the number 0. If you go back to the top left part of the screen, I have 0 to 9 for decimal, 0 and 1 for binary, and 0 to F for hexadecimal. We always start off with 0. So here, the least significant bit would be 2 to the power of 0, and then moving on to the left would be 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. What does that mean? It means that the least significant bit has a value of 1, then moving to the left, the next bit has a value of 2, the next bit moving to the left has a value of 4, the next bit moving to the left has a value of 8. Why is it 2 to the power of n for each bit, the value for each bit? Well, 2 because there's only 2 numbers, 0 and 1. Okay, so looking at this example here, we notice that as you move to the left, you start increasing. It's just multiplying the number that you start off with by 2. So 1 that we start off with times 2 is 2. 2 times 2 is 4. 4 times 2 is 8. If we had a fifth bit on the left, that value would be 2 to the power of 4, which is 16. So if we have 2 bits, if you can see in the bottom left corner, this stores a combination of 0, 0, 0, 1, 1, 0, 1, 1. There are 4 numbers from 0 to 3, and the equation would be 2 to the power of n minus 1. The minus 1 is not in the power. So the n represents how many bits are there in your problem, in your equation. So here it would be 2 to the power of 2 because we have 2 bits minus 1. 2 to the power of 2 is 4. 4 minus 1 is 3. So these 2 bits could go up to the number 3. Now we move on to the right, and you have 1, 0, 1. What number is this in decimal? Well, you got the short method, which is method number 1. You have, remember, the third bit to the left, which we'll say that bit number 1 is the least significant bit. Then moving to the left would be bit number 2, and bit number 3 would be the most significant bit. Remember, the 3, if you look at the top, is 2 to the power 2. Okay, then we have a 0 on the second bit, so we wouldn't add 2 to the power of 1, or in other words 2. But then we have a 1 on the least significant bit, which is 2 to the power of 0. Any number to the power of 0 is 1, has a value of 1. So 2 times 2 to the power of 2 is 4. 4 plus 1 is 5. this binary number is 5 in the decimal number system. Okay, what is the longer method? These two methods are really just one, but the reason that I'm showing this longer method is because it's necessary to learn this for the hexadecimal number system, which I'll talk about shortly. So I said because there's a number 1, there's a value of 1 in the most significant bit, it's 1 times 2 to the power of 2 plus the next bit, which is 0. 0 times anything is 0, so we don't take that into account, plus 1 for the least significant bit times 2 to the power of 0. And then we basically start off the first method, the short method, which is 2 to the power of 2 plus 2 to the power of 0, which is 4 plus 1, that's 5. So using 1 bit, we could only go from 0 to 1. We only have 2 numbers. 2 bits, on the other hand, consist of 0 to 3. As you can see in the top example, we have 4 numbers, 0 to 3. 3 bits consist of numbers 0 to 7, a total of 8 numbers. 4 bits consist of 16 numbers for a total of 0 to 15. So if you look at the top where we have the 8, the 4, the 2, and the 1, if each bit if we have 4 bits, if each bit had a value of 1, add the 8, the 4, the 2, and the 1, that's 15. That's how you know that 4 bits could store the max value of 15. And again, looking at it from the numbers 0 to 15, there are a total of 16 numbers. So the hexadecimal number system. So the equivalent value of 0 in hexadecimal is 0. Then the equivalent 1 in decimal would be 1 in hexadecimal, 2, 3, 4, 5, 6, 7, 8, 9. But you see, when it comes to 9 moving on to 10 in the decimal number system, right, we have a 0 before the 9. Okay, and here we would be resetting the 9 to a 0, but the 0 that's on the left of the 9 would increase by a unit of 1. So now from moving from the value 9 or 0, 9, we would be moving on to the value of 10. So the value 10 in hexadecimal is A. B is equivalent to 11, C is equivalent to 12, D is equivalent to 13, E 14, F 15. But once we get into 16, the F resets, which is what I just finished explaining. The F resets to 0, but the 0 which is to the left of the F increases by a unit of 1. So that 10 in hexadecimal is not 10 in decimal. That 10 in hexadecimal is 16. And then you keep increasing the least significant number by one increment of 1 unit, and 1 1 would be 17, 1 2 would be 18, and so forth. So now I'll show you an example of how can we get an equivalent number from hexadecimal to decimal. Well, if we have the number, for example, 5a, and as you can see, these are all just two-digit examples. 5a. So we said before that in binary we had 2 to the power of n. Well, because we have 16 numbers in hexadecimal, again 0 to 15, we replace the 2 to the power of x with 16. So now it's 5 times 16 to the power of n, which is 1. That 5, remember, the a was 2 to the power of 0. The 5 was 2 to the power of 1. But now we're replacing the 2 with 16. So 16 to the power of 0 is still 1. 16 to the power of 1 is 16. So we multiply the 5 times 16, gives us 80. 10 times 1 is 10. You add, it's 90. Okay, now what happens if we have 35 in hexadecimal and we're trying to find the equivalent decimal number? So it's 3 times 16 to the power of 1 plus the next value of the 5. 5 times 16 to the power of 0, which is 1. You add that, 48 plus 5, 53. Okay, what happens if we have FB? F represents the number 15 in the decimal number system. So 15 times 16 plus B, which is 11 in decimal. 11 times 16 to the power of 0, which is 1, is equivalent to 240, which we get that from 15 times 16, plus 11, which is 11 times 16 to the power of 0, which is just 1. 11 times 1 is 11. So 240 plus 11 is 251. What about D7? D is equivalent to the number 13 times 16 to the power of 1. 7 is 7, so 7 times 1, you get 7. So 208 plus 7 is not 98, but 215. Okay, so this is again from hexadecimal to decimal. What about if we were trying to go from hexadecimal to binary? Well, it's still a bit tricky. Not really. I find it easier, but okay, let's take a look at the same numbers. So 5. Each digit in hexadecimal consists of 4 bits. So it takes 4 bits to represent one character in hexadecimal. Why is that? Well, remember we said 4 bits goes up to the value of 15. The max value that we could get with one digit in hexadecimal is 15. What character is that? It's F. Okay, F goes up to 15, and we said 4 bits goes up to 15. So it takes 4 bits to represent one digit in hexadecimal. So we look at 5A. Okay, 5 is 0101. A is 10, which is 1010. Okay, so we said that this has a value of 1, this has a value of 4. Okay, 4 plus 1 is 5. That's how we represent 5. This bit represents 8. Then we have 4, right? But we don't take that into account because it has a 0. We have the 1, which stores an element of 2, and then we have 1, but we don't take that into account either because it has a 0. So 2 plus 8 is 10. And as you can see here, I have an example of how we could mathematically prove that 1010 is 10. So looking at 35 in hexadecimal, 35 is 1 plus 2, which is 3, and then 4 plus 1, which is 5. Okay, FB. F is 15. So we have to use all 4 bits to represent the number 15 in hexadecimal. That is why these 4 bits are all ones. But B, on the other hand, B is 11. B is 8 plus 2 plus 1. 2 plus 1, 3. 8 plus 3, 11. D7. 7 would be 1 plus 2 plus 4. 7, we don't use an 8. D is 13. So we have 1, 4, and 8. 8 plus 4, 12. 12 plus 1, 13. And there you go, folks.